These are the notes for the homework that precedes Unit 3. See here, it says Unit 2, Unit 3. We're doing the notes right in between Unit 2 and Unit 3. There's a page of notes here and then 2 pages of homework. And the notes are pretty straightforward. What we're doing is we're just introducing here a new notation. The notation is referred to as differential notation, invented by Leibniz. So differential notation is just another way to write the derivative. So we can write this notation for the derivative. So y and then y prime means the derivative. We have function notation, so f prime is the derivative. And the new notation is right here. It's the dy dx. The dy dx, the dy is standing for delta. So if you remember, we got the slope, we got rise over run. The slope is the change in y over the change in x. And now the notation we're using to write that is dy dx, change in y over change in x. Just another way of writing slope, just another way of finding the derivative. So example 1, if we want to find the derivative of this, well, we're going to use the power rule. So then we're going to multiply 12 times negative 2/3, which is going to give us negative 8. And then we're going to take the x squared and we're going to knock it down by one exponent, and we're going to end up with the derivative, or dy dx, is equal to negative 8x to the 11th. Pretty straightforward. Here we have q is equal to 8 divided by p to the 5th. We could rewrite this as 8 times p to the negative 5th, put it in a form where it's easier to use the power rule. And then what we're doing is we're taking the derivative. Now the derivative, we're not working in x and y, we're working in q and p. And what we're saying here is that for every change, for this change in p, delta p, there's a delta q that goes with it. So we've got the change in q over the change in p, dq dp, which is then going to be equal to negative 40 times p to the negative 6th, or if we get rid of the negative exponent, we put, we put p to the 6th, that's a plus, p to the 6th in the denominator. All right. Example 2. Here what we have is we have an equation that is not written in normal y equals notation. Right? This is standard notation. What we're looking for is dp over dq. So what that means is we want to find how it is that p changes when q changes. So p is the dependent variable and q is the independent variable. So we're going to take this and we're going to solve it for p first. So we'll get 5p is equal to 2q plus 20, and then divide everything by 5, and we get p is equal to 2/5 q, 2/5 q plus 20, and then we're going to take the derivative of this, or the other way to say it is we're looking for the slope. How much change in p do we get for every change in q? And dp dq is equal to 2/5. Here we're looking for q to be the dependent variable and p to be the independent variable. So if I get a little change in p, how much change in q do I get? So we're going to take this same equation and we're going to now solve it for q. We're going to make q the dependent variable, and this is going to be minus 5p over here plus 20 So then Q is going to be equal to positive 5/2 P minus 10, and the slope of this, or the derivative of this, the dq dp is equal to 5/2. All right, everybody doing okay? So, continuing on again, the notation, this ds dy notation, is helping us to decide what's the dependent variable, what's the independent variable. So we're looking here. What this is, if we were to graph this, right? So we have the square root function that looks like this, and this is my dependent variable here. This is my independent variable here. We're looking to see, with a little change in w, how much change in s do I get. So I'm going to find the derivative of this, and the derivative is change in s over the change in w, ds dw, which is going to be equal to 1 over 2 root x. If we flip this around now and we're looking for the change in w, for every little change in s that we get, then we've switched our independent and dependent variables, and now this, our independent variable, is s, our dependent variable is w, and what I want is I want to take this and solve it in terms of s. So I'm going to get w is equal to s squared, right? And this graph would look like that. So then dw ds is going to be 2s. Now, the thing that the differential notation does for us, which is going to come in quite handy, is that differential notation behaves just like fractions. So if you take the change in x divided by the change in y, and you multiply it by the change in y divided by the change in x, these differentials, the delta x, delta y's, the differentials, they just behave just like functions, just like fractions. So dx dy times dy dx is 1, right? So the symbols behave like fractions, right? Which allows us to do some more complicated mathematical notation. So here's a problem about a pebble that's dropped into a pool. You got a ripple. The ripple spreads out. The area of the circle is defined by pi r squared, obviously. And we have this relationship. We know that the radius is equal to the time cubed. So after 1 second, the radius is 1. After 2 seconds, the radius is 8. After 3 seconds, the radius is 3 cubed. Right? And we're going to work in centimeters here. So if we're looking for the change in the radius over a period of time, right? So we got a little change in time. How does that change the radius, right? So we're doing r versus t. R is our dependent variable, t is our independent variable. So then we're going to take this equation here and find the derivative of that. So dr dt is going to be equal to 3t squared, and we're going to put units on this too to help us see what's going on here. So the radius, the change in radius, is defined here as 3t squared, and the units are, the radius is changing in centimeters per second. Delta r is measured in centimeters, delta t is measured in seconds. Now if we want to find how the area changes as the radius changes, area is the dependent variable, radius is the independent variable, we're going to use this equation up here. We're going to find the derivative. So dA dr is going to be equal to 2 pi r, and the units here are dA is measured in centimeters cubed, centimeters squared, and the radius is measured in centimeters. And this is centimeters squared of area divided by centimeters of radius. Now, remember up here, these derivatives work, these differentials work like fractions. So now if I want to find dA dt, I can do this in two ways. The first way I can do it is I can figure out what a is in terms of t. So if a is equal to pi r squared, I'm going to leave that open because this is where the r is going to go. Now, my r I've defined as t cubed, so I'm going to tuck t cubed in here, since r is t cubed, and then simplify this, and I'm going to get the area is equal to pi t to the sixth. And then what I'm looking for is I'm looking for the derivative of this. So dA dt, right? So this is dependent variable area, independent variable time. dA dt, is going to be equal to 6 pi r to the fifth. Right? So this is one way to do it. Second way to do it is here. We're going to take dA dr. Well, I found dA dr. dA dr is right up here. It is 2 pi r and times dr dt. Now, the reason I'm doing this, I have dA dr, which I found up here. I have dr dt, which I know is right here. And if I multiply these two together, notice that the dr's reduce to 1, and that leaves me with dA dt, which is what I'm looking for. So if I take dA dr, 2 pi r, and I multiply it by dr dt, which is 3t squared, then I end up getting 2 times 3, 6 pi r to the fifth. Right? Same thing. And thus ends our notes, and you have a couple pages of homework to do.